Hello everyone. Today I'm going to talk about duality, the concept of duality. So in order to make it more clear in the same context that we were teaching the course for the previous parts, so first we talk about duality in linear optimization. And then we talk about duality in nonlinear optimization. So all of the facts that I will talk about in the linear optimization part only apply to linear programming. And the methods that we used before, simplex algorithm, so you can apply that to the dual problem as well. So the original problem or primal problem in linear programming was formulated in this standard way. Minimizing C transpose X are our variables. This is the vector of variables subject to some inequality constraints and this. So in order to translate this into the dual problem, what we are going to do, first, we have A matrix. So we are going to find A transpose. Then we have C transpose here. We are going to use C transpose transpose. Then we will have an inequality constraint here. The new variables for the dual problem are y. So all of y's should be positive, and the objective will be maximizing B transpose y. So our variables are y. Alright, the question here is what are the y variables, right? So y variables are nothing but the Lagrange multipliers for these inequality constraints. So that's the reason that all of y's should be positive. And these are some ground rules of how to translate each of these constraints into their corresponding constraints in the dual problem. So the primal problem gives us the solution to X. The dual problem gives us the solution to Lagrange multipliers. Alright, now the question is, why do we need to find the dual problem in the first place? What's the main motivation to find the dual problem? And the answer for linear programming is dual and primal will have the same objective function value. So that's very interesting. It means that if you solve this problem and find the optimal values of y and then you insert them in the objective function, it will give you the same value as when you solve this problem, you find the values of x and then you insert them in the objective function. This is the fact that we call it zero duality gap, because always there might be a gap between the solution of dual problem and primal problem, but for linear optimization, it has been proved that the dual and primal problem have the same answer. In order to see that how that happens, let's try to find the dual problem of the dual problem. I will repeat that. So we have the primal problem. So primal problem is basically a linear optimization problem. Now we have the dual problem. Now what I want to find is dual problem of the dual problem. Alright, let's follow the same ground rules. First of all, I'm going to translate this into the original form that we had. We want it to be in minimization form. So I'm going to say minimizing minus B transpose Y subject to, I just multiply both sides of this by minus 1, so it will be minus A transpose Y is greater than equal to minus C. And Y is greater than equal to 0. So this is still your dual problem. Now we want to find dual of the dual problem. If you recall from the previous step, you have to find transpose of this elements. Let's see how it looks like. So it will be maximizing minus, so we transpose this and bring it to the objective function. C transpose, let's say Z. So we have X, Y, and Z. We want to find the values of these, subject to. So now we have to find the transpose of this coefficient, this matrix. So it will be minus A. It's already minus A transpose. We have to find this transpose. Multiply by Z is less than or equal to. Again, we are going to look at the objective function, the coefficients that appear in the objective function. I'm going to find their transpose, so it will be minus B transpose, transpose. And then because the Z's are Lagrange multipliers corresponding to an inequality constraint, they are all positive. So let's try to simplify this a little bit further. So I don't need the dual problem anymore because I could find the dual of dual problem. Let's simplify this a little bit more. We want to write it into the form of a minimization problem. So it will be minimizing C transpose Z. Z are our variables, subject to. So here we have negative A transpose transpose. So transpose transpose is the same as the original matrix. So negative A. Negative B transpose transpose. So it's negative B. I'm going to multiply both sides of this by minus 1. So it will be AZ greater than or equal to B. Z. Okay. So this is dual of dual. Let's go back and see what was our original problem. Our original problem, or the primal problem, was minimizing C transpose X subject to AX greater than equal to B and X greater than equal to. Alright. You can see that if I solve this and I find the values of these, this is equivalent to solving this and find the values of X. So what it tells me that dual of dual problem in the linear programming part, in the linear programming problems, is the same as the original problem. That's why if you solve the dual, it's equivalent to solve the primal problem, and they will both give you the same set of answers. So let's keep the original problem here. So there are a few facts that we have to notice. One is number of variables in the primal problem is equal to number of constraints in the dual problem. And the same thing for the constraints. Number of constraints in the primal problem is equal to number of variables in the dual problem. So we explained the reason earlier. The reason is number of variables in the problem, in the primal problem, show the number of Lagrange multipliers in the dual problem. So it means that I have the same number of constraints as the variables in the original problem. And let's say I have 10 constraints in the primal problem. It means I need to have 10 Lagrange multipliers. Those Lagrange multipliers are going to be the variables that I can find by solving the dual problem. Okay, we are good in terms of time. Okay, so now there are some rules for each type of constraint or variable in the problem, in the primal problem. So, rule 1. Primal problem is a minimization problem. Minimization problem. Then it gives me that the dual problem is a maximization problem. Rule number 2. Equality. So when I use this symbol, I refer to equality constraint. Equality constraint unlimited dual variable. So if you recall, in the example that we solved, we didn't have equality constraint. So we have to make sure that all of the Lagrange multipliers should be positive. But if we have equality constraints in the primal problem, it means I need the lambda, which is an unlimited variable, in the dual problem. So rule number 3. Inequality constraint, if it's greater than or equal to, it's a positive dual variable, greater than equal to 0. Rule 4. Inequality constraint less than or equal, it's equivalent to a negative dual variable, less than or equal to 0. Now let's look at the variables. If we have positive variables here, okay. Before writing this, if you remember, I said dual of dual problem is equal to primal problem in linear optimization. So in order to see what we have to replace for positive variables, we can come here and say, okay, I have positive dual variables. What happens? I have inequality constraint. So if you have positive variable, we will have inequality constraint. That's going to be less than or equal. And rule number 6. Negative variables less than or equal to 0. Again, you will have inequality constraint, but this time greater than or equal. And for the unlimited variable, it's exactly the same as the equality constraint. So the last rule, rule number 7, if you have an unlimited variable in the primal problem, it translates into an equality constraint in the dual problem. All right, given all of these rules, now what I'm going to do, I'm going to try to apply this to an example. This way you will have a better idea of how to apply it. So if the primal problem is minimization, the dual will be maximization. If you have equality constraint, it means you have an unlimited dual variable. If you have inequality constraint, it leads to positive or negative dual variables. If you have positive or negative variables, it refers to inequality constraints in the dual problem. And unlimited variables in the primal problem means an inequality constraint in the dual problem. Because, again, just to emphasize, if you have equality constraint, their corresponding Lagrange multipliers could be either 0, negative, or positive. Alright, example. Minimizing x1 plus x2 minus x3 subject to 2x1 plus x2 greater than equal to 3, x1 minus x3 equal to 0, x2 plus x3 less than or equal to 2, x3 positive, x2 negative, and x1 non-negative. Okay. Now, first of all, we are going to find C and A matrix. So here, C vector is 1, 1, negative 1. It's basically the coefficients of these variables in the objective function. In order to find A, what we have to do, we have to make sure that we make all of these constraints either in equality form or in the greater than or equal to form. So this is already in the right shape. This is in the right shape. I'm going to rewrite this as oops, sorry. So you just write A because we are not going to change the order of this. So A will be 2, 1, 0 for the first constraint. For the second constraint, it will be 0. This is x1, x2, x3. For the third one, you have 0, 1, 1. Alright, now that we have A, you can simply find A transpose. So 2, 1, 0, 1, 0, negative 1, 1, 0, negative 1, and 0, 1, 1. And you also can simply find C transpose. What's the value of B? B here is 3, 0, 2. Okay. Now we have to figure out what's the nature of the constraints at the dual problem. All right. So this one is an inequality constraint and it's greater than or equal to, so it refers to a positive dual variable. This one is an equality constraint, so it will lead to an unlimited variable. This one is a less than or equal to constraint, so it will lead to a negative dual variable. This one is telling us that x3 is greater than or equal to 0, so we need a less than or equal to constraint. This one tells us x2 is less than or equal to 0, so it tells us that there should be a constraint greater than or equal to. And this one, x1 is unlimited, so there should be an equality constraint also. So these rules help us to portray how our dual problem looks like. Alright, now we have to find the dual problem. So we have minimization here, so we will have maximization here. We will have B transpose Y. So, first of all, we have three constraints, so we only will have three Y's. Y is equal to Y1, Y2, Y3. Now I'm going to find B transpose 3, 0, 2 and multiply it by Y. So it will be 3Y1 plus 0 Y sub 2 plus 2 Y3. And now we have A transpose, so let's multiply A transpose by Y1, Y2, Y3. We already know our constraints. So we will need an equality constraint, we will need greater than or equal to and less than or equal to. Equality, greater than or equal, less than or equal. So, and this side, it will be C transpose. So you already have C, 1, 1, negative 1. So we have 2, 1, 2, 1, 0, 1, 0, 1, 0, negative 1, positive. Multiplied by Y1, Y2, Y3 is equal, greater than equal, less than equal to 1, 1, negative 1. So it gives us the set of constraints 2y1 plus y2 is equal to 1, y1 plus y3 greater than equal to 1, minus y2 plus y sub 3 greater than equal to negative 1. We also know some information about the limitation on y's. So we know that y1 is positive, y3 is negative, and y sub 2 is unlimited. Alright, now you might have a very valid question of how I determine this one is referring to an equality constraint. So, when you want to find the dual of dual problem, if you recall, we have to come back to the original problem. So x1 here should refer to the first constraint. So what's the feature of x1? x1 is unlimited, right? So x1 is unlimited, it means it refers to an equality constraint. That's why constraint number 1 here is an equality constraint. Then we have x2 is a negative value. So if you recall in the rules that we listed, if in the primal problem you have x2 negative, it refers to an inequality constraint like this. And I expect x3 is positive, right? So x3 is positive, so it refers to a less than or equal to constraint. That's what I have here. So this originates from x3, this originates from x2, and this originates from x1. Just as a hands-on example, what I suggest you do at home is to find the dual problem of this dual problem and try to see if dual of dual problem, so forget about this part, only look at the constraints that you have and the objectives. So this is your objective, these are your constraints, and these are your variable limits. Only look at these three and try to find dual of dual problem. And then see if the dual of dual problem is the same as this original problem. That's a good practice to go over the rules that we discussed, and also try some hands-on example in terms of variables, changing this into the minimization problem or maximization problem, and so on. So that's all for the duality for now. I'm going to post another video and solve more examples of duality in linear programming. Thank you.